Hello and welcome to another example video. This is Winter 13, ON13, paper 41, and it's about electron diffraction. So let's read the question. We have electrons traveling at the speed v in a vacuum. Okay, so electrons traveling at speed v in a vacuum are incident on very thin carbon film as illustrated in this picture. Okay, so there's a fluorescent screen here. Right. So if we know that electrons will have wave property, when the electron passes through the tiny gaps between the atoms of the carbon film, you will observe some diffraction pattern. Okay, so the emergent electrons are incident on a fluorescent screen, and a series of concentric rings is observed on the screen. So in the theory video, I explained why there's a concentric ring, and I managed to find simulation for you to see what is going on. Okay, so the link to this video is, I guess, hopefully somewhere down in the description. Okay, or you could visit this website. Really cool animation in the entire channel. Okay, shameless. I mean, I am plugging them. Not that they would know me, but yeah. So anyway, here we are going to show you the wave particle duality. All right, and there'll be some sound. So turn on your speakers. How else are you listening to me, right? So you notice a few things. Number one, if it's a particle, right? Okay, so we pass it through some slits. So this is a double slit, but of course, if we put a carbon film, there are many gaps between the carbon atoms. Okay, and if let's say we think that electron is a particle, we kind of like expect that the particles will collide with the fluorescent screen almost randomly. So there's no distinguished pattern. You just get maybe an entire green spot like this. Okay, but if let's say it is like wave, let's say I send a sound wave or a light wave through slit, the diffraction pattern that I'm expected to see based on this interference will be bright dark fringes. So this one from your AS is pretty familiar. But things get very weird when it's in the quantum realm. So to represent this in the simulation, they actually use like a cloud, but it's hard for us to even imagine what is happening. So when the quantum object, in this case the electron, is sent to slits, the wave will become a particle when touching the screen. So the electron become a wave, which will become back to a particle when it hits the screen. So life is very trippy. So if we repeat enough times, you will still get those bright dark fringes. And if let's say I rotate the screen 360 degree, this is what we will get, the concentric rings. Okay, so that would be the observation of the experiment. So suggest why the observed rings provide evidence for wave nature of particles. So the concentric ring is an evidence of diffraction. So you get that bright dark fringes. You form the rings. You have bright, you have dark, bright, dark. So this ring, if you sweep 360 degree, this bright dark fringes, you will form a ring. Okay, so you will say that the circles, concentric circles, are evidence of diffraction. Evidence of diffraction, which is the spreading of wave. And after that, you can say diffraction is a wave property. 1 mark each law. Okay. Right, moving on. The initial speed of the electrons is now increased. State and explain the effect, if any, on the radii of the ring observed on the screen. So again, we have already covered this in your lecture, but I will give you a framework about how to think. So we are increasing the speed. Okay, and when we increase the speed from P, momentum is equal to mv, momentum increase. Okay, and why do we want to talk about momentum? Because we want to look at the radii of the ring. So I want to comment on the diffraction pattern. Did the diffraction pattern become more or less spread out? Okay, so if the momentum increase from the equation lambda is Planck constant over momentum, your lambda will decrease. Okay, so if lambda decrease, there's less spreading of the pattern. So because of this, I can say the radii decreases. All right, so once you have this framework outside, you scribble somewhere, now you can write. You can state and explain the effect. So let's state first. As velocity or as speed increases, speed of electron increases, is increased. Okay, the momentum increases. Okay, so from lambda is equal to h over p. Okay, wavelength of electron. It never feels quite right when I write wavelength of electrons, but it's correct in this chapter or in the world of quantum physics. So the wavelength of electrons decreases, and because of this, the radii decreases. Okay, so that's all. Just mention wavelength of electron decreases, radii decreases. So your 3 mark will be number 1, momentum increase. This is your first mark, momentum increase. Your second mark is when you mention something along the line that because momentum increase, wavelength decrease. Okay. And finally, you will say that the radii decreases. To answer the question, state and explain the effect. All right. So that's part 1 or question 7, part A, B. All right. Next. A proton and electron are each accelerated from rest through the same potential difference. Determine the ratio of the de Broglie wavelength of the proton to the de Broglie wavelength of the electron. I pronounce it wrongly now. It's de Broglie. De Broglie. Can even call it de Broglie. De Broglie. Yeah. De Broglie wavelength. Okay. So what we're looking for is lambda for proton over lambda for electron. Okay. Now to find lambda, we need the momentum. Okay. So I'm going to start by first stating all the obvious things that I need, because this is 4 marks. So you kind of expect multiple steps. Number 1, lambda is equal to h over p. So from this, wavelength of proton to wavelength of electron is equal to momentum of electron over momentum of proton. Inversely proportional, we will flip it. Okay. I can do a TikTok video, but so much. You do one and send it to us. Okay. So if it's inversely proportional, we will flip. Okay. Moving on. Next, we know that momentum is mass times velocity. So I'm going to write this one here. Lambda p over lambda e is the mass of the electron, which we can find in the first page of the exam paper, multiplied by the velocity of the electron, mass of proton, velocity of proton. So what remains here is for us to find the ratio of the velocity of electron to the velocity of proton. You may be thinking, Miss, they're accelerated through the same potential difference, and they both have the same charge, which is, the magnitude of the same charge, which is either positive or negative 1. Wouldn't that mean they have the same speed? No. It means that they have the same work done by electric field or electric potential energy. So from here, I'm going to change color a bit. Same potential. I can say that the change in KE is equal to the change in electric PE. Okay, so we are talking from rest, so this is half mv square. Change in EPE is QV. All right, so from here, I can say Q is constant. Proton is positive 1, electron is negative 1. Magnitude is the same. Same accelerating potential, constant. So what I have now is mv square is proportional to constant. Okay, so if mv square is proportional to constant, and I want to find VE over VP, I can rewrite my ratio such that VE, if you are struggling a bit with this because you're not familiar, that's also okay. Bring this around, so this is proportional to constant ma. Let's say the constant is K lah, doesn't matter. K over M. Okay, so if we are going to continue this, I'm going to write here, okay, running out of space, V square will be proportional to 1 over M. So I can write V over V. Now I'm going to pick a bit to see which one I want. VE over VP. Whole thing square is equal to inverse, flip again. E over P become P over E. Okay, so I want to substitute this. I'm just going to do this. Square root MP over ME. Okay, so VE over P is root MP over ME. I'm going to continue here. Lambda P over lambda E is ME over MP times VE over VP is square root of MP over VE. MP over ME. Okay, so let me zoom out again so you can see the substitution a bit clearer. You can see clearly now. All right, so what I did was I substituted VE over VP here to this one, because VE over VP here is equal to square root of MP over ME. All right, so now what remains is to simplify and substitute. Okay, so I can continue this and I can say lambda P over lambda E will be, okay, I just bring all of this into square root lah. So if I bring this into square root, this will be ME square over MP square. Okay, I bring this into square root, multiply by MP over ME, put bracket. So from here, I can tell that this one will cancel out. And what I have left is ME over MP power half. Do I know the mass of the electron? Why, yes. Can copy in front. 9.11 times 10 to the power negative 31. Do I know the mass of a proton? Why, yes. 1.67 times 10 to the power of negative 27. Okay, so once you find the mass of the proton, the mass of the electron, you can press your calculator. And don't forget to square root. We nearly forget. Power 1 over 2. So this will be 9.11 E negative 31 divided by 1.67 E negative 27. Square root answer 0.0233. I guess I could write 2.3 times 10 to the power of negative 2. If you want to write another SF, it's also okay. So I guess I can write this as 2.33 times 10 to the power of negative 2. Yeah, that's right. So what did we learn here for these 4 marks? Okay, quite a lot of steps. I'll label them for you. The first mark you will get if you use the equation lambda is H over P. Logic, right? This is one of the most important. Okay. Second step, you know how to use the conversion of Ke to electric Pe. So this part here, you got 1 mark. All right. Third step is based on this, you come up with the proper ratio of this one based on these two relationship lah. Okay, so how you arrive at it, you can use substitution. I like to use proportionality. Okay, so when I use proportionality, the way I do it is I define the constant. So for example, if I'm talking about this one, H is constant, so lambda and P is inversely proportional. Okay, so lambda P over lambda E is PE over PP. Okay, if you're not good with this kind of ratio, an alternative way of writing this, right? Again, this is just for you. Is that you can use lambda P over lambda E, or I guess lambda P, whoops, wow, the lag. Okay, I write here to decrease lag. All right, so here you have lambda is H over P ma. So lambda electron is H over momentum of electron. Similarly, lambda proton is H over momentum of proton. Equation 1, equation 2. You go and take 1 divided by 2 lor. So what happens when we have 1 divided by 2? Lambda electron over lambda proton on one side. This will be H over momentum of electron over H over momentum of proton. Chop the H. So 1 over PE over 1 over PP. Don't crack a joke. Don't crack the joke. Okay. And you can see the inverse relationship where it's being flipped. If you know what joke I'm talking about, that's great. If you don't know, it's fine. You're not missing out on anything at all. I wish I don't know the joke. But this is the inverse relationship. So after a while, you can actually skip this step. And when you see this, you can write this ratio. Likewise, when you see this half mv squared is equal to qv, and your qv is constant, and obviously half is constant, you can immediately tell mv squared is constant. So it's even quite easy to jump from here to here. And the reason why we want to substitute the velocity is because we know the mass. Mass can copy from formula in front, but we don't know the velocity. And there's no way to know because you don't know what the accelerating potential is. So you need to use ratio and divide. So once you divide already, okay, you just bring this one and put inside VE over VP. Put inside here, and then after that it's a matter of simplifying and substituting. So if your final answer is correct, you get 1 mark. Okay, and also the other mark is when you substitute the right value and you have this formula. So 1 mark is here, and then the other mark is here. All right, cool. That's it. This is a very classic de Broglie equation question. First part, they walk you through why this experiment is important. It shows the wave property and what happens if I change the accelerating potential. Okay, then we know this electron got wavelength, but the wavelength depends on momentum. So if I accelerate a proton and an electron from rest, what would be the ratio of their wavelength? So you can tell here that the wavelength of a proton is greater than the wavelength for electron. Yeah, and no, wait, wavelength of proton is less than the wavelength of electron. Let me write here. Because this one is less than 1. Okay. So this thing here is less than 1. If you're wondering why I'm writing highlighter, it's because they don't let me change pen. Okay, as previously mentioned, because this ratio is less than 1, lambda proton is less than lambda electron, because this is the ratio of lambda P over lambda E. So this means proton is harder to show the diffraction pattern. That's why this diffraction pattern, currently the only way to do it reliably in the lab is by using electrons. That's why we had to wait for someone to discover the electron first. So this lambda P is less than lambda E, so diffraction pattern less spread out. If let's say you do the double slit or the carbon film electron gun electron diffraction thing. Let's spread out for proton compared to electron. All right, so that's it for the question. All right, it's not that difficult. It's a pretty classic one. Make sure you understand the setup and what the observations mean. Okay, and also normally if it's a 4-mark calculation, there is probably multiple steps. Okay, so I've labeled the steps. This is step 1, which I kind of, okay, that was obviously a lag. Okay, hashtag pray for my computer. Anyway, step 1, you think of, if you want the Broglie wavelength, what is the relationship? So there are a few tools you can use. One I list down for you lah. It may be very overwhelming. Number 1, have you used momentum is h over lambda? Number 2, momentum is mass times velocity. Number 3, velocity is equal to, okay, so this one needs to use conservation of energy. So we will use the equation of half mv square is equal to qv, work done by electric field. So from here you rearrange, or you can find the value of q lah. All right, so it's like a Russian doll situation. Conservation of energy will give you velocity, velocity will give you momentum, momentum will give you wavelength. All is good in the land of quantum. Simple calculation. All right, so that's it for this example. If you find this helpful, share and like and subscribe to us. Okay, let us know what you think. I'll see you in the next one. Take care. Do more questions. Grind. And let's ace our A2s together. Bye-bye.